co-host here today for Research Rounds. I know I've seen previous talks by Jenny, and I know you're in for a treat today. Jenny has been the chief scientist at the Challenging Environment Assessment Laboratory here at Toronto Rehab since 2009, since before it existed, I guess. As part of the home community team, her work supports our objective of finding ways to help people get out into their communities, whether that's on foot or in their vehicles. We know we need people to get out of their homes and engage with their communities. For instance, it's been known for a long time that people who have hearing loss fall more often, but we don't know why, and Jenny's work is trying to answer that question or learn more about that question. Her work is also trying to understand how we can support older adults as they need to continue driving longer. So her work is looking at understanding how all of our senses integrate in our brains to understand how to keep driving safely. And on a personal note, I think I want to say that Jenny is one of the kindest people I know. And most recently, I would credit her with a recent grant that our team put in to support our winter footwear testing work. And I'm convinced that it's a result of your careful editing and suggestions that got us that grant. So, and I'm sure people in the room that know Jenny would agree with that. So with that, I'll turn it over to Jenny Campos.
Thank you, Tillich, for that lovely introduction. It's so nice to be giving a talk in front of a sea of familiar faces and to see a packed house. I said it for the benefit of the people online. I said I'm going to say it's a packed house whether it is or not because they can't necessarily see how full this is, but I'm actually quite pleased with the turnout. So thank you guys for coming. So the work that I'm going to talk to you about today is a little bit of a snapshot of some of the work that we've been doing together as our sort of, I would call our mini research group that's part of the home community team that we call the Multisensory Integration in Virtual Environments group. So you'll see a group of us at lunch the other day, and then I superimposed some people who were not able to come to lunch, but who are active parts of our team. Tillich mentioned that I'm the chief scientist of the Challenging Environment Assessment Lab, which I think everyone here is familiar with. Some people on the line might not be, but clearly this is a collection of simulators. Our group is really interested in using simulators for a variety of research projects, not all of them, but a lot of them. For one reason is to actually look at the interplay between different sensory systems. So virtual environments or simulation allows you to sort of change the relationship between what you see and what you hear and what your motion detectors are telling you. Sometimes we just want to make the experience more realistic. A lot of what we want to do, just like a lot of what everybody in this room wants to do, is translate our research from lab to life. And so in order to do that, using something like virtual reality gives you that element of realism and introduces challenging situations in a more realistic way, including a multisensory, multimodal way. And then our group is also very much interested in optimizing simulation. So there's a lot of applications that use simulation, that use virtual reality. So how can we make those interfaces and those experiences more valid for assessments and testing and more usable for a variety of applications. So that's why we kind of have aligned ourselves with looking at using and optimizing virtual environments and with a multisensory lens. And that's what I'm going to focus on today. So what do we mean when we talk about multisensory integration? Well, this really just means how does the brain integrate all of this information from touch, from hearing, from vision, from our vestibular organs or acceleration detectors in our inner ear. How does it do that? And how does it do that so effortlessly and simultaneously? And here's a picture of the brain that is sort of common or familiar to a lot of people, where it looks quite compartmentalized. So you have your visual cortex that's focused on visual processing, you've got your auditory cortex focused on auditory processing. Is that really the way it is? Is it really that compartmentalized? Or is the brain really quite multisensory in nature? And what we're learning more and more is that there's a lot of interconnections in the brain, even at a very low level, that supports multisensory integration. So we think of multisensory integration as being particularly important for those types of activities you see on your right, which are these, or your left, which are these sort sort of extreme athletics or highly sort of tasks with high levels of expertise. But clearly in all of these tasks that we're doing every day, the ability for you to sit up right now, eat your pizza, listen to what I'm saying to you, that's obviously all, you're able to do that by integrating senses. When you have a conversation with somebody, you're not just listening to what they say, you're actually looking at the movement of their mouth, and that changes your experience of language and comprehension completely in many cases. So I like to give a few examples for people who are maybe not as familiar with some of these multisensory interactions. And illusions are a really good way to do that. So there's different types of illusions depending on the different sensory combinations we're talking about. So I thought I'd make this research rounds a little bit interactive. So visual auditory illusions, visual proprioceptive illusions, and visual vestibular illusions. How many people are familiar with the McGurk effect? Okay, so enough people in the audience are not familiar with the McGurk effect, so I think it's a fun one to start with. So we'll switch here to YouTube.
Watch this experiment. It's the McGurk effect.
Ba, 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 ba.
What do you think he's saying? If you think he's saying da, da, da,
Or da,
you are
da,
in the
da.
grand majority. But now, close your eyes and listen instead of watching.
Ba, 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 ba.
The voice is saying ba, ba, ba. Now, let's replay it without the sound.
And we don't need to do that. So how many of you got that illusion? How many of you, when you were watching him, had a totally different perspective on what he was saying compared to when you were just listening to him? With your eyes closed. Okay. So I won't show you the second one because we did start a little bit late. This one is going to be tricky to do because you're eating pizza, but let's try it anyways. So the crossed hands confusion is a fun one to do in partners. So team up with someone you're sitting beside, and we'll take turns doing this, okay? So one person out of the two, copy me. So put your hands out straight, face each other, grab them, and flip them in. Okay. So the second person, the partner, without touching a finger, without touching their finger, point to one of their fingers, and the person with the crossed hands has to wiggle it as quickly as possible. Don't touch it. Don't touch it, just point. Okay, now instead of pointing, now touch the finger. Instead of pointing, now touch the finger, and see if that changes things. Okay, and so that we make sure it's fair, let's get the next partner to try it, and I'll show you again how to do it. Hands out, facing, cross, in, and flip up. And now point without touching, and wiggle as quickly as possible. And once you've mastered that, then try touching it and see if it makes it any easier. Okay. So how many people found it either they wiggled the wrong finger or they found that it required more cognitive effort to wiggle the finger when their hands were crossed? And how many people found it easier once you had that additional tactile feedback, basically to help solve the problem for you? These are the things we take for granted. You know, your hands usually on your right and on your left, and when you mix them around and you change the relationship between what you see and your proprioceptive information, it doesn't take much to confuse the brain, despite the fact that we're doing this effortlessly. And and one last illusion that I'll mention, because it is most relevant for a lot of the work that I do, is the train illusion. And if you take the train like I do, well, that's very dramatic music. Somebody's hold. Yeah, somebody put me on hold. Okay. So the train illusion, if anybody commutes like me, and I'm coming from Burlington every day, a couple times a year I'll be sitting on the train, and the train beside me starts to move, and I perceive that as my train starting to move, when my train is in fact stationary. And so that's the global visual motion, which usually happens when you're moving through space, but it's happening when you're stationary, and so your brain has to reconcile that ambiguity. And so there's various ways that the brain can do that. So here are the basic rules of multisensory integration. By the time you leave today, you will all be experts in multisensory integration. So the first rule, these are not shocking. These are not shocking revelations. The first one is that combining redundant information from multiple senses increases perceptual precision. You typically get better or more precise, or you have more sensitive perceptions when you have more than one. But sometimes one is more reliable than the other. Maybe vision's more reliable than hearing for certain tasks, and the more reliable sensory information is weighted higher in the brain. It's given more weight. So how do you determine when and if multisensory integration is going to occur? It doesn't necessarily always have to occur. It's more likely to occur if the two sensory inputs are aligned spatially. So if two things happen generally in the same spatial location, they're going to be more likely to be assumed as being caused by the same event and therefore integrated. Same thing with the temporal rule, but this case in time. If things are aligned in time, they're happening simultaneously or perceived as happening simultaneously, they're going to be more likely to be attributed to the same object or event and therefore integrated. Causal inference, this is something that's often learned over sort of a history of your experience with the world. So if you hear a bark and you see a dog, then you would assume that those things are going to be causally related because your experiences over life and be more likely to be integrated. And then the principle of inverse effectiveness, which is sometimes a little bit counterintuitive to people, is that when you have two weak signals, your visual information is sort of, is not particularly reliable, and your auditory information is not particularly reliable, you are going to be more likely to integrate those signals than if those signals are both strong. And when you think about this intuitively a little bit more, it makes sense, because if your visuals were really strong, you don't really need that auditory input as much to contribute to your percept, because your vision's doing a pretty good job, and same with the auditory. But when they're both kind of not so reliable, you don't have that sensitivity, then you can rally the troops and you can really benefit from having those multiple signals. And the amazing thing is that these principles of multisensory integration are evidenced at the level of a single neuron in the brain. And so if you're presenting stimuli visually or auditorily and you're measuring the responsiveness of a single multisensory neuron in the brain, you see evidence of these principles applying, and then of course we see them applying in the context of behavior. So what our research has been most sort of focused on and interested in in terms of our sort of MIVE team has been looking at multisensory integration in the context of mobility or self-motion perception. So looking at how vestibular information is integrated with vision, proprioception, and auditory information as we move through space. So a lot of times we talk about this sort of broadly speaking, we're interested in how these things support mobility in terms of supporting standing balance, supporting walking, and supporting driving. Think of it along that spectrum. So when everything is functioning fine with all of your sensory systems, you think we're pretty good at using our rich visual world to support us, our good sort of hearing abilities to support us. But the thing is that the world is challenging. The world is messy. Things are moving. Things change unpredictably sometimes. And so, again, making use of this redundant multisensory information to make sure that when vision is perhaps a little poor, like when driving at night or in the dark, then maybe you're using other cues to help augment that visual information. Those are the types of things that we're interested in studying a lot of the time. And that's not to mention what happens when sensory systems start to fail a little bit, when you start to experience some vision loss or some hearing loss, among other things, vestibular loss, changes to the musculoskeletal systems and proprioception, then clearly that sort of adds to the sort of challenges in which we're using and then integrating our sensory inputs. So one of the things that we've really been primarily interested in looking at recently is whether or not there are age differences in multisensory integration. So as you go from younger adulthood, we haven't studied too many children, but younger adulthood into older age, are there changes in the way that the senses are being integrated centrally? So irrespective of whether or not we're having declines in our individual sensory systems, which certainly come into play, the way in which sensory information is being integrated, does that change as well? And so there's been some speculation as to why that makes sense, that perhaps we may expect changes in integration as a function of age. One relates back to that principle of inverse effectiveness that I mentioned originally, which is that if you have weaker sensory signals, then the benefits of combining sensory information could be increased. And so there would be a hypothesis that you would actually expect heightened multisensory integration as a function of age, because you're getting these declines in the sensory systems, in their sensitivity. And that doesn't necessarily mean clinically significant hearing loss, clinically significant vision loss, but really even just sort of the sort of typical age-related declines in the sensitivity of those different sensory systems. And so when you get kind of, again, this reduced sensitivity, combining might make more sense. And of course, there's other things that change with age in terms of attention, less of an ability to inhibit irrelevant information that also comes into play. So not to simplify this too much. And indeed, there has been some previous work by others to show that there does seem to be something to this idea of heightened multisensory integration. This is just one example. Pfeiffer and al. Have shown that if you just present an auditory stimulus to a younger and older group of subjects, and just a visual stimulus to older and younger group of subjects, basic flash and beep type stimuli, then you get this sort of redundant cue advantage when they're combined in the multisensory. This is a reaction time measure, so they get faster. Reaction time is reduced when you have two senses versus one, and you see that for both older and younger. But you see that the multisensory advantage, and you can see my cursor, you can see that the multisensory advantage is greater for older adults than it is for younger adults. So they benefited more in terms of having faster reaction times when they had 2 versus 1. So this is all fairly recent research, and there's a lot of open questions. So some of the things that we were interested in is, do these results that we see from these sort of basic flash and beep tasks translate, first of all, to more sort of complex, realistic, everyday tasks, but also do they extend to other sensory combinations? So there's been a lot of work, probably the majority of work, in visual auditory integration, and we're very much interested in things like visual vestibular integration. So the two sort of clusters of studies that I'll talk to you about today, the first one is looking at multisensory contributions during driving and self-motion perception. And then the second one will look at the contributions of hearing, the effects of hearing loss on mobility. And this is all related to what Tillich talked about in terms of increased falls risk. So everybody, a lot of people in this room know Robert. So as a part of Robert's PhD thesis, he used a multisensory driving task to look at how having different sources of sensory information during driving affected driving performance. So this was done before Driver Lab ever existed. So if you're wondering why that doesn't look at all like Driver Lab, it's because we had a little mock-up of a car that was housed in Street Lab for this study. And we had the visual information that was projected over the projection system, auditory input, which I'll describe in a second, and then the vestibular or the motion input was provided through the motion platform. So the task was super, super simple. It was just maintain a speed of 80 kilometers an hour and stay in the center of your lane. Those were pretty much the instructions. And then the participants drove through multiple drives, a practice and then 4 experimental drives. And there were 3 different conditions, just visuals. There was no sound, there was no motion. Visuals plus auditory. So the auditory sound was the tire roar, the wind, the engine sounds, which ramped with speed. And then visual vestibular or visual motion. And so that's when the motion platform is activated. And the metrics I'll tell you about today were the mean speed, the speed variability, and the variability in lane keeping. So this is kind of what that would look like. in the simulator. So you can see on the bottom part of your screen the driver's perspective, and this is the visual plus motion task. So you can see how the motion simulator moves in response to the visuals. And so like all simulators, hexapod-based simulators, the movement that is being introduced by the person steering and the gas and brake activity is being translated to an approximate motion that would stimulate the vestibular system in a comparable way as what you would experience in the real world, as much as possible, that being the caveat. Okay, so if we first start off by looking at variability in speed, on your left, you've got the younger adults clustered, and on the right, the older adults. This is standard deviation in speed. And the first thing that you'll see is that for the younger adults, the reduction in variability came with added auditory cues, so having those additional auditory signals made them less variable in the speed that they maintained. No real difference when we added motion, but you see that that difference was bigger. First of all, with the older adults, when they had vision alone, they were much more variable in their speed than were younger adults. But you can also see that adding the visual or the auditory cues reduced that to a significantly greater effect, and that adding the motion cues also reduced that, making them less variable. And we saw a similar pattern with sound cues. A similar pattern with mean speed. And so when we just looked at the overall mean speed that they kept, because they were told to keep it at 80, older adults slowed down when auditory information was presented. And younger adults didn't show that same effect. Then when we look at the variability in lane keeping, again, the younger adults clustered here, the older adults clustered here. See, that's cut off. We see that it didn't actually make much of a difference at all in younger adults. I should say that we wouldn't expect lane keeping really to be affected by the presence of auditory information, so that was kind of a check. And so we didn't see that in either group. We saw sort of a small reduction in variability for the younger people when we added motion, but we actually saw an increase in the variability when we added motion in the older adults, which was a little bit puzzling. So we'll come back to that. So to just summarize those main effects, we found that older adults showed greater effects of having additional sensory inputs during driving than did younger adults. That was evidenced by the slower mean speed and reduced speed variability with sound and motion for the older adults. But this added vestibular input, or these added sort of motion inputs, increased variability in lane keeping in the older adults. So why is that? And we sort of played around with lots of different hypotheses, but we settled on a couple of more reasonable ones. So the first one is that, as I mentioned in my caveat, when you have a simulator, you can do as best as possible to make sure that the information you're presenting visually and via motion is as congruent as possible. But the thing is that when you're limited by a particular motion envelope, and when you can't expect how somebody's going to respond in the simulator, then you can never always ensure a one-to-one mapping with that. And so for most young people, I mean, Bruce can tell you, these are motion cueing algorithms that have been developed over decades. And so for most young people for whom these are typically tested on, they can deal with those incongruencies, and it doesn't seem to affect their behavior. But it could be the case that if the older adults are integrating those signals more and or differently, and if they're not able to adapt to these incongruencies, then it might actually affect their performance negatively. But because this is a driving task, and age is typically sort of confounded with driving experience, it could mean that because older adults just have a longer lifetime history of driving, they have a longer learned history of what happens when they steer a car or use a gas pedal. And so those sort of hard-coded expectancies with respect to how the driving simulator was going to react as related to a real car could have also affected their performance. And so in order to kind of strip the driving experience out of the equation, we did a sort of stripped-down psychophysical heading discrimination task. So I'll just describe this one quickly, and I won't go too much into the results, but I think it's an interesting paradigm and provides some clarity to that driving data. So the first thing that we wanted to know was, do older adults and younger adults optimally combine visual and vestibular information in this kind of stripped down version? But because we were triggered by the driving data about these sort of sensitivities to the incongruent visual vestibular information, we also wanted to introduce systematically conflicts between vision and vestibular in the older and younger group to see if we would have different patterns of responses. So this was a very, very basic task. I'll demonstrate it. Ready? So we moved them in one heading direction, and then we moved them in another heading direction, and they had to say which of the two heading directions was more to the right. So that was a very sophisticated demonstration. So really it was just two movement intervals, which was more to the right. So we did this with just visual information alone via head-mounted display and just using an optic flow stimulus. We presented this with with just vestibular information alone, so no visuals, completely in the dark, and just gave them the same physical motion profile. Or we gave them both of those combined, so the visuals combined with the motion. And that's what I'm summarizing there. And then we plot the psychometric function. So for people who are not familiar with these, here I'm plotting percentage of rightward responses, so how many times people say more to the right. So, and here is the actual heading direction. So when it's 20 degrees to the right, 100% of the time you should expect people to say more to the right. When you're 20 degrees to the left, you should pretty much 0% of the time people should say that was more to the right. But then as you get to these smaller angles of difference, it becomes more difficult to differentiate which one was more to the right. And so then you start getting to a situation where people will start saying 50% of the time more to the right. So what this data gives us is it gives us a sensitivity because the slope gives us an indication of how precise people are at making these judgments. And so going back to the sort of predictions of multisensory integration, if you had just the visual alone trials represented in the blue curve and just the vestibular alone trials represented in the pink curve, if you combine those two things, you would predict that that slope would get steeper if people were getting more precise with their estimates with the combined. But also we can look at the shifts along this axis in terms of where that 50% point is, or that point of subjective equality, and that gives us a sense of how they're weighting different information. But in order to do that, we have to be tricky. And as I said, we have to sort of provide them with conflicting information. So in our Q conflict trials, which they were never told existed, we would present them with a physical motion that was always straight ahead, but visually we would move them either 5 degrees to the right or 20 degrees to the right. So either a small visual conflict or a large visual conflict. And we wanted to see how they would respond. So I'm not going to show all the graphs and everything. I'm going to just sort of summarize the key findings. So when you just look at the unisensory conditions, just vision alone and vestibular alone, both older and younger adults estimated heading equally well with vestibular cues alone, but the older adults were worse than younger adults when using vision alone. When they were combined and congruent, both groups, integrated visual and vestibular cues optimally. So we saw that increase in precision that you would expect when you had 2 versus 1. But when we introduced sensory conflicts, the integration did start to break down. But the breakdown happened at smaller conflicts for older adults. So the younger adults still tolerated that 5-degree conflict. They broke down at 20 degrees. The older adults did not tolerate that 5-degree conflict. And while younger adults always weighted the more reliable input higher, and we know the individual sensory reliabilities because we measured the unisensory reliabilities in each subject, the younger adults pretty much always weighted their more reliable cue higher, but the older adults gave disproportionately more weight to the visual cues, which, as I said at the beginning of the results, were poorer than the vestibular cues. So they sort of showed this non-optimal weighting as well. And these results are sort of in line, sort of in an indirect way, with that increased variability in lateral control of older adults in the simulated driving study if we were to attribute that to their inability to deal with subtle incongruencies that happened during the simulation. So what this means is that for older adults, even slightly mismatched visual and vestibular cues could give rise to more variable estimates of self-motion, which may then manifest as greater performance variability during self-motion tasks like walking and driving. Okay, so in-term summary for the sort of multisensory integration driving and self-motion perception, we can say that older adults did show some evidence of heightened multisensory integration. They seem to rely more on visual inputs, or at least their percepts and their behavior was affected more by multiple inputs, but they had these lower tolerances to sensory conflicts, even subtle ones. We like to think about this in sort of an, like a broad sense about how this could apply to real-world applications. So some things we've talked about are implications, for instance, to vehicle design. So if you think about how vehicles are being designed currently, apart from these automated vehicles, they're looking at sort of having increased sound attenuation inside the car, increased adaptive suspension, and so what that is doing essentially is it's isolating people from important sensory inputs that could be used to support their driving. And so if older adults are relying more on these multisensory cues, by removing those as sort of viable options to augment their perceptions, their visual perceptions, you could actually be putting them at greater risk by causing them to sort of misperceive their speed and other aspects of driving. Of course, it's got some implications for the use of simulated environments. Almost everything that we know of today in terms of the development of virtual reality, virtual environments, and simulators is with young, healthy people or middle-aged people. And so if this is going to be a problem, especially in this older cohort who are arguably going to become the biggest users of these simulator technologies, then we need to be really sensitive to this effect. And then, of course, for people in this room, it could have implications for rehabilitation. So when you're thinking about rehabilitating somebody after a stroke, traumatic brain injury, etc., thinking about taking a multisensory approach to rehab could be advantageous. So I'll take a quick break here to see if anybody has questions. Katrina.
With respect to the lane keeping, I noticed in the video that the shadow of the person moved, and it reminded me of that silly thing when you're going into a parking lot and there's a low door and you're sitting in a car that's not too short, or not too tall, but you, the driver, duck as you go under. And so I was curious whether you're monitoring their kinematics as well as their self-reported perception.
So Katrina's question is, are we monitoring their kinematics in addition to their perception? So in that driving study, we weren't. In the psychophysical heading task, we made sure that everything was fixed. So they they weren't able to have those kinds of head movements. Very good question, because that has a lot of relevance, obviously, to the vestibular input that they're receiving. Any other questions? No? Okay. So then I'll move on to the effects of hearing loss on mobility. So changing gears. Pun intended. Okay, so a few facts about age-related hearing loss, and that's primarily what I'm going to be focusing on, is age-related hearing loss. So some people are surprised to hear that hearing loss is the third most prevalent chronic health condition in older adults. Here's its sort of estimated prevalence by age, and so by the time people are in their 60s, almost 50%, 44% are experiencing some degree of hearing loss. By the time you get to 80 years and older, you're looking at around 90%. So this is a very common problem. Tillich mentioned that the hearing loss, mobility, and falls link has been long known. That is not true. I think that was my error maybe in communicating with Tillich. It's actually it's very recently been identified. And I think that anybody here who looks at sort of research that is identifying falls risks, and if you look at public campaigns associated with increasing safety and decreasing falls risks, hearing loss almost never features on that list. But because of a lot of large population studies more recently, who have looked at sort of these epidemiological links between hearing loss and falls, it's becoming more and more obvious that there's a clear link here. But this is only fairly recently. But going back to 2006, I found this pretty interesting, that a Statistics Canada report indicated that individuals with hearing loss more commonly reported limitations related to mobility and agility than limitations in communication, memory, or learning. Again, back to these sort of epidemiological studies, it's been shown that those with hearing loss are more likely to develop difficulties with walking than those with normal hearing. They walk slower, have poor physical functioning, and are at increased risk of frailty. Critter et al. Showed that of older adults attending audiology clinics that they surveyed, 70% had a prior history of falls, with 50% having fallen in the previous year. And individuals with even mild hearing loss had 3 times greater odds of falling than their age-matched peers, and they were at more risk of experiencing injuries requiring medical attention. And this is, I think, a really important feature, is that there's a dose effect. So there's a 1.4 times greater odds of falling for every 10 dB of added hearing loss. But there is some light at the end of the tunnel, or some reassuring news that the use of hearing aids may improve balance, but this is all very new and somewhat speculative. Okay, so why is this? This doesn't seem entirely intuitive. So it could be because you have unreliable spatial sound cues to support orientation and spatial navigation. Clearly we get a lot of information from our sound environment that can support that. It could be that people who have age-related hearing loss also have age-related vestibular loss. They are both in close spatial proximity, they work in similar ways, and they have shared nerve inputs to the brain. So maybe they're paralleled in those individuals. We know that there's age-related vestibular loss, we know that there's age-related hearing loss, but we don't necessarily know whether or not those two things are linked within individuals. It could also be that increased listening effort that comes with hearing loss reduces the cognitive resources that are available to support things like mobility. So when you have to work really hard to listen to something, then being able to do 2 things at once, like listen and walk at the same time, could be compromising to that second task that you're trying to do, including mobility. It could be due to social isolation. You have hearing loss, you get physically and cognitively deconditioned because you are not engaging as much as you would typically. Or there could be some common pathological cause. So the 2 that I'll talk about briefly right now are 2 that we've investigated. The first is that there could be this comorbid link between hearing and vestibular loss, and the second one relates to this increased listening effort, sort of dual task cost hypothesis. Sorry, I got a alert. Okay, come back. Okay, so we'll start with the listening effort hypothesis. So I think it's clear to everybody in this room, but to a lot of people, it's not sort of intuitively accepted that walking requires cognitive resources. We think this is being largely automatic and not requiring many cognitive resources. Everybody here knows that's not true. Again, listening loss may result in this increased listening effort, which may then actually use up cognitive resources that could be supporting other things. So when these cognitive resources are taxed by hearing loss, doing 2 things at once becomes more difficult, such as having a conversation while walking. So this was work done in collaboration, Kathy Bacor-Fuller and Karen Lee, Allison and Sim Tung, who many of you know. So we did this in Street Lab. We first started off by looking at people who were younger and older with normal hearing, where we used our virtual Toronto database and we simulated a street crossing, so crossing University Avenue. But while you're crossing University Avenue and your kinematics are being measured using the motion capture, 3 of your friends are talking to you at the same time. So there's 3 people speaking 3 sentences, and you're going to have to listen for a target word in one of those sentences. I'll describe this in a little bit more detail. So we had 3 tasks. One was just stand there and do the listening task alone, just listen to your 3 friends and respond. One was the walking task alone, just cross the street, don't listen to anything else. And one was walking while listening at the same time. And here are the weird sentences that we use, but are very commonly used in this field, which is coordinated CRM reference something sentences. So they take the form of ready, insert some call sign. So that could be Ringo, Hopper, Charlie. So ready, call sign, go to, a color, number, now. So an example target sentence would be, ready, Hopper, go to white 2 now. And you might be prompted to say, okay, your target word is Hopper. And so you have to listen for the word Hopper and then repeat the color and the number that came after Hopper in that sentence. Sounds hard. It is kind of hard, but when you get used to it, it becomes a little bit easier. So we also made it a little bit harder or easier by manipulating cognitive load. So in the lower load, you were always certain, you were told beforehand that that target word was going to come from the front speaker. So I said there were 3 speakers, one was on the right, one was on the left, and one was in the front. So you would be told beforehand, okay, it's always going to be that center talker who's going to be telling you your target word. So you could zone your attention in and listen to that talker and try to ignore the other 2 talkers. So that would be a lower load situation. But in a higher load situation, we wouldn't tell you where that talker was going to come from, where that target was going to come from. So on 60% of the times it would come from that center speaker, but on another 40% of the time it would come from the left speaker. So that would mean that you'd have to distribute your attention and listen to all of the talkers and then pick out your target talker and give the color number. So here's what the listening. So the target word will come up in the middle of the screen.
White 6.
Try it, see if you can get it. Tiger.
Ready, tiger, go 1 now. Red 5.
Does anybody get it? It's really hard. It's hard under these circumstances in particular. Here's what it would look like walking. So here's Sintung demonstrating. So you can see that as she's walking on the treadmill, then the visuals are updating as she's walking. But there's no listening task. And then the listening while walking, it was both at the same time. So we looked at 2 sort of categories of measures. One was listening performance, just percent correct, and then one was walking performance. So we wanted to see, whether or not they were more variable in their steps, whether or not they showed changes in the pitch of their head and things like that during the single task and dual task conditions. So the questions were there age-related differences in dual task costs? And if so, did the younger and older adults exhibit different dual task trade-offs to listening performance, to walking performance, which was prioritized? Okay, so what you see here is in white is the older adults, in black is the younger adults. So clearly across the board, and we'll go through each of them, the older adults, this is listening performance, this is percent correct. So the older adults did worse in the listening performance overall than the younger adults, so that's the first pattern. But then if we look at on your left, the certain, so this is when they always knew where the target was going to come from, versus the uncertain, which is on your right, you can see that the performance went down as expected. So when you have to spread your attention, you become worse at getting the listening accuracy. When we look at the dual task costs, so when we look at the left 2 clusters and compare it to the right 2 for listening alone versus dual, then you see that the younger adults show some dual task costs, but in the white bar, these older adults show a greater dual task cost. So when they had to do 2 things at once, they had a greater cost to listening. When we look at head pitch, we see that for the younger adults in black, it really didn't make a difference if it was just the walk only versus when they had to do the listening while walking under certain or uncertain conditions. But when we look at the older adults, they actually took a more upright head pitch. So this is forward head pitch that's plotted here. And so you can see that the forward head pitch was reduced when they had to do two tasks at once. And we also saw that in stride time variability, when they were just walking alone versus doing 2 things at once, at least in a certain condition, the older adults actually had reductions in the variability of their stride time compared to the younger adults, who showed a slight but non-significant increase in stride time during dual task conditions. And so what this showed was that the older adults displayed the greater dual task costs in listening than in the walking. They exhibited this more upright head alignment and less variability in stride time during dual task compared to single task conditions, which is sometimes surprising to some because those would be evidence of having perhaps better walking stability during dual task compared to single task. So when you have greater load on the system, they were actually showing some improvements. But there are theories of postural prioritization and cognitive compensation that are probably fairly familiar to people in this audience, where it seemed to be perhaps, if we're looking at these dual task costs, then the older adults were allocating greater resources towards their gait over their listening performance when the cognitive demands got high and they had to allocate weights to the different demands accordingly. So then very quickly I'll show you that we did this again with older adults with hearing loss. You can see there's their audiograms across the different frequency, the normal hearing in black and the hearing loss in white. And so across those frequencies we saw greater hearing loss in the hearing loss group. We did the same conditions again, but in this case we couldn't use the 3-talker version of the task because it was too hard. So our people with hearing loss just couldn't do the 3 talkers. So we did 2 talkers, and we had the certain again and the uncertain again, but only from 2 possible locations. So for the normal hearing group, the age-matched peers, this is a little bit of an easier task in terms of the listening part of it than what I just showed you. And so the first thing to look at here, this is listening performance, percent correct again. In the black is the normal hearing, and in the white is the hearing loss. So I just sort of put boxes around these so that you can see that pretty much, again, across the board, people with hearing loss had poorer performance than people with normal hearing. We also saw that when we considered the sort of certain versus uncertain comparison across the board, both the normal hearing and the hearing loss group again showed this reduced performance in the uncertain, but there were no dual task costs in this case. And then when we calculated the dual task costs by subtracting the single task from the dual task and plotted them here, and here again we've got certain and uncertain, certain and uncertain for the normal hearing in black and the hearing loss in white. Anything above this line would be considered a dual task cost. Anything below this line would be considered a dual task benefit. And so you can see for the slightly more difficult listening task, the older adults with normal hearing showed this dual task benefit. So again, it could be that when you're sort of primed to have to do 2 things at once, then you may actually have sort of increased arousal that could be benefiting performance, not necessarily detrimental. So clearly there's this trajectory whereby some sort of dual tasks or secondary tasks are going to have no effect because they're simply not sort of taxing your cognitive resources. Some are going to have a potentially beneficial effect by sort of increasing alertness, arousal, or sort of upregulation, and then some are going to have a detrimental effect. So it's interesting to look at those maps and those trajectories and how they shift for different populations. And then for the head pitch, we just really saw the same thing in both groups. So there was reduced head pitch during dual task compared to single task, and there was less variable head pitch as well, which I'm not showing here. And then for the stride time variability, we did see a group effect here. So we didn't see an effect with respect to the dual versus single task in either group, but we did see that the people with hearing loss, again represented in white, had a higher and much more variable across subjects stride time variability compared to the individuals without hearing loss. So, summarize, those with normal hearing were better able to perform the listening task than those with hearing loss. Both groups performed better under more certain conditions. The normal hearing group demonstrated a dual task benefit to listening, while the hearing loss group did not. And both groups demonstrated this more upright and less variable head position during the dual task conditions. Those with hearing loss also demonstrated that overall more stride time variability than those with normal hearing. Okay, so very quickly, because I've only got about 5 minutes left, I'll tell you about this last study that we did to look at vestibular sensitivity in people with hearing loss, with and without hearing loss. There's our collaborators there, and this work was done by Josh. So this was done in Stair Lab, and we put people in this box. It doesn't look super comfortable, but we squished them in with lots of padding to make sure that their head was fixed. Gave them some blindfolds and some noise-canceling headphones, so we stuck them in this dark Stair Lab in a box. This is like the most challenge for this study was making sure people weren't claustrophobic, and then also making sure they stayed awake, which I'll explain in a minute. So we had younger adults without hearing loss, older adults without hearing loss, and older adults with hearing loss. The important thing to note is that they had no known vestibular or cognitive impairments. We did audiometry to measure their hearing, otoscopy to make sure there weren't any middle ear problems, and then we did end organ testing of their vestibular systems, including VAMPs and VHITs to look at otolith and canal functioning. And then we did posturography as well. So we looked at center of pressure path length with eyes open, on compliant foam, with eyes closed, and with eyes closed and ears closed, which just means headphones on. So we did a movement detection task, and we did it in heave and pitch. So we basically rocked people up and down, like bounced people up and down like this for heave, and then we rocked people like this for pitch. So now you know why people couldn't stay awake. And then what we did was we presented with 2 movement profiles, and they just had to say which of the 2 was faster. And so it would look something like this, and they had to say second. And then what we did is that we made the difference between those 2 movements smaller and smaller and smaller and smaller until they could no longer detect the difference between those 2 movements anymore. And then what that gives us an indication of is how sensitive their vestibular system is. Because if people can get to a magnitude of difference that is bigger, that means that, and they can't distinguish it anymore, their threshold is lower, is higher. But as soon as you can get down to those smaller differences, then that means you're more sensitive, more precise. And so that's what we used as an indication of vestibular sensitivity. And so here we've got, this is the result for the pitch detection, so detecting this pitch motion and angular velocity. And we have the younger adults, the older adults with normal hearing, and the older adults with hearing loss. So you can see there's some variability, but there are significant group differences between the younger and older the older with and without hearing loss, indicating that as a group, the older adults with hearing loss were less sensitive, detecting differences in their movement. And we saw this also for the detection threshold for heave, but only the difference between the older adults with and without hearing loss, not the younger end compared to older. This was somewhat verified also through the posturography. So eyes open all the way to eyes closed and ears closed, which would be sort of increasing in difficulty, center pressure path length. The older adults with hearing loss, you can see, really are situated quite far above the other 2 groups. And we do see some age-related effects as well, which are commonly known. So older adults demonstrated reduced sensitivity in detecting heave motions than younger adults and pitch. Oh no, in older versus younger, sorry. And then the hearing loss group demonstrated reduced sensitivity to heave and pitch detection compared to the normal hearing peers. And then the hearing loss group demonstrated less stable standing balance, particularly under those more challenging conditions. So to overall summarize the hearing loss mobility piece of the story, we can say that audition interacts with other sensory and cognitive processes to support mobility, that concurrent walking and listening produce different trade-offs at different cognitive levels and levels of difficulty. Some individuals with age-related hearing loss may also have reduced vestibular sensitivity and poorer standing balance. When we think about this in terms of applications and interventions, I think it's clear that what's starting to emerge is that routine screening for falls risk in individuals with hearing loss is warranted, that hearing screening in fall prevention clinics or people who are at risk of falls is warranted, that hearing devices such as hearing aids should consider spatial sound cues that support self-motion perception under more realistic acoustical, multisensory, and cognitive conditions rather than isolating their assessments to a sound booth. And that training with these devices should include active exposure to and exploration of a wide range of realistic acoustic and multisensory conditions, including mobility-related tasks. So a lot of the focus in hearing aid development is speech comprehension and not in noise, and so we need to sort of maybe broaden the goals of hearing aid manufacturers to include supportive mobility. And of course, never to forget dual sensory loss. So as you get older, you're going to be more likely to have hearing loss and also declines in your other sensory systems. So overall summary, important to consider multisensory contributions, I would argue, to self-motion perception. And there are differences in cue combination and sensory integration as a function of age, but there's clearly a lot to be explored with respect to these sensory cognitive interactions across these different developmental trajectories, and then also in the face of sensory and cognitive loss. There could be something to be considered for sort of these isolated silos with respect to assessment that are being done by individual medical professionals, whether it be neuropsychologists separate from audiologists, separate from ophthalmologists, separate from physiotherapists. So having sort of an inclusive assessment, or at least communication among these professionals or assessments is probably warranted. And this is something that we're working on also as a part of our Canadian Consortium for Neurodegeneration and Aging group, which is really trying to look at this within the context of dementia. So to sort of put sensory issues at sort of the forefront of the consideration of these, how it interacts with cognition. And some of you may have seen a recent Lancet Commission paper that looked at potentially modifiable risk factors for dementia, and the number one potentially modifiable risk factor was hearing loss. So something also to keep in mind. And with that, I thank you.
It's a couple minutes after 1, so I think we'll end it here today, but thank you so much, Jenny, and if people have questions, I'm sure they can approach you. Thanks again for joining us today.